Okay, this will be A-level chemistry quiz for week 10. I mean, it's not that hard. It's a bit long. That's it. Okay, well, let's start. Okay, question 1. We have butanine, excess hot concentrated KMnO4. This is very simple. We know that. Okay, let me just draw this a bit better. Uh, you have carbon is connected to two hydrogen groups right there. And you have a carbon that's connected to one and an R group. So we have an R group, oops, an R group, and we have a hydrogen group. You know that reacting this side with KMnO4 will give you CO2 plus H2O. This side, when it reacts with that, it will give you an aldehyde. I'll just draw the group. Basically, it'll give you an aldehyde. Oh my bad. Give you an aldehyde, which then further oxidizes into a carboxylic acid. And so the answers are carbon dioxide and a carboxylic group right there. And the R group, see, there's another carboxylic, there's actually one carboxylic group. The R group will be CH2CH3. That's the R group. And yeah, CH3, CH2. This only has CH3, which is wrong. Okay, next, question 2. So this is actually pretty easy. We did this in IGCSE. This is alkane with UV light. Alkane with a halogen in the presence of UV light. Alkane. It will be free radical substitution. And I think this is self-explanatory. So we have methane, and then chlorine can substitute with this, with that, with that, and HCl can be produced by homolytic fission. Like when we're substituting that, and let's see electrons go to each side, we're gonna have a positive carbocation with a H plus here, and then it reacts once one of the chlorines, um, once one of the chlorines separate by homolytic fission. This becomes a free radical and it reacts with HCl to produce HCl. And the others, you just substitute Cl. For this one, it's going to be a positive carbocation reacts with another positive carbocation, and this results in termination of the reaction, so it won't react anymore. So these will just bond together to get CH3, CH3. Okay, next. Question 3. Carbocations, okay. What is the hybrid orbital of the carbon behind the positive charge? So the hybrid orbital, you have to count the number of domains. There's S, there's 3 domains. This is S, P, and P1. Same thing here. There's a hidden hydrogen here. 1, 2, 3. So there's 1, again 1, 2, and the R group 3. So it's sp2. Next. To see the type of carbocation, you count the number of R groups. So for example, for this we have there's 3 R groups, so it's going to be tertiary. For this is only 1 R group, so it's going to be primary. For this is going to be secondary, since there's only 2 R groups. There you go. That's easy. An SN1 reaction. SN1 reaction is only for tertiary and secondary. Oops. Most tertiary, but they're asking for the most probable. It can be tertiary and secondary, but the most probable will always be tertiary. Tertiary will always be SN1, so it'll be this one. The least stable, you have to memorize this. The least stable is the primary. It's due to the amount of alkyl group. See, here there will only be 1 alkyl group acting on the carbon, while here there's going to be 3, which makes it more stable. So a positive inductive effect on the carbon. Okay, compound C4H9Cl. One of the isomers. Okay, so this is a halogen alkane reacting with KCN. So this will be nucleophilic substitution. So it'll be substitution nucleophilic. Okay. CN and KCN acts as a nucleophile. A nucleophile. Uh, a nucleophile is an electron-rich species, so it just has a lot of electrons. Now, give the name of the product of the reaction. So when this reacts with KCN, it says it has an SN1 reaction. So what are we looking for? We are looking for an isomer of C4H10Cl, which has a positive carbocation. Which one is that? It will be this one. Cl will be here, and C carbon. So it'll be CH3. Oops, CH3, CH3, CH3. So what is this? This this carbon right here, it has three R groups. One, two, and three R groups. And then since Cn replaces Cl, it will replace it like that. The intermediate will be a tertiary carbocation. And what reaction takes place here is an SN1 reaction. Um, yeah, so the CN will bond to this one to carbon here and lose its positive charge, and that's how you get it. So to summarize, if it's an SN1 reaction, they want the isomer that has a tertiary positive carbocation, which will be this isomer, and then cyanide replaces Cl to give this. And the thing about KCN reactions, it's very useful in chemistry, is I've read in the book, it says that it increases the length of the carbon chain, and I guess it works because look, in CN, previously there's only four, but now there's five carbon. There's this carbon, that carbon, this carbon, that carbon, that carbon. Okay, and naming the compound is easy. There's two methyl groups, and you take the longest chain, so it's methane, ethane, propane. So it's propane with a nitrile. Oh, for nitrile compounds, you always start with the functional group. That's, yeah, for nitrile groups. So it's gonna be propane, nitrile, and then there's two of these on the second carbon atom. So it's gonna be two dimethyl propane nitrile. Okay, easy. Next, question 4. This is pretty easy. Hydrocarbon A, let's just count 1, 2, 3, 4. That's a butane. There's no double bond, so yeah. This is methane, ethane, propane, butane, but it's connected all together, so it's a cyclobutane. What else? Hydrocarbon C. Okay, this is easy. You take the longest chain, so it's 1, 2, 3. It can be one. It can be here as well. Doesn't really matter. So let's say that's propane. And then it's on the second carbon atom. There's gonna be two methyl propane. Yeah. Okay. The molecular formula. This is an alkane, and alkanes are CnH2n plus 2. So if there's four carbon atoms, it will be C4H10. For cycloalkanes, the functional group will be CnH2n. So for cycloalkanes, will be CnH2n. This is a new one. We have never, I think, learned this before, but there you go, CnH2n. Hydrocarbon C. You can just count the amount of carbon. So it's 1, 2, 3, 4. How much group? There's 3 hydrogen there, 3 hydrogen there, 3 hydrogen there. 1, 2, 3. There's one more hydrogen here. 3, 6, 9, and there's 10. So it's gonna be C4H10. The hydrocarbon and their isomers are A and C. They have the same what's it called? I think it's molecular formula. Yeah. The general molecular formula for cycloalkanes is gonna be CnH2n. Okay, that's easy. Next. How long has it been? 9 minutes. Okay. Okay. Crude oil is a mixture of hydrocarbons that extract from Earth's crust and separate in different fractions. Okay, C5H12 is an alkene, which is saturated. Saturated, that means it has no double bonds. And the functional group of alkanes is CnH2n plus 2. Okay, next. For this one, they want for the incomplete combustion. The incomplete combustion, it will always give you CO plus H2O. For complete, it will give you CO2 plus H2O. But they're asking for incomplete, so it'll be this one, CO plus H2O. And then you just have to balance it. Catalytic converters are installed in car exhausts, okay. Carbon monoxide and nitrogen monoxide are examples of gas pollutants and chemical reaction. Okay, the chemical reaction between carbon monoxide and nitrogen monoxide. So I'll write it up here, CO plus NO. It will give you CO2 plus nitrogen. You have to memorize this. And the thing about carbon monoxide is it's toxic to humans. It will take up space in the hemoglobin of blood cells, I think, and oxygen won't be able to bind efficiently. So carbon monoxide is toxic to humans, and yeah. And for nitrogen monoxide, it can cause what's it called? Acid rain. It can cause acid rain, and these are really bad things for humans. So that we convert them to CO2 plus nitrogen. Oops, nitrogen. Yes, nitrogen is in the air. It's very harmless. But carbon dioxide, it's less harmful than CO and NO by a big amount. Even though it does contribute to global warming, it does it at a very slow rate. So it's not that harmful. Okay. Catalysts used in catalytic converters, the most used is platinum, but then there's also palladium and rhodium. So there's platinum, palladium, rhodium, but platinum is the one that has the one that is most used. Okay, so an alkane, the next question is an alkane reacting with a bromine. An alkane reacting with a bromine is the one reaction we did before, which is free radical substitution. And it only occurs in the presence of ultraviolet light. And it is a nucleophilic substitution. No, I mean not a nucleophilic, I'm sorry, a free radical substitution. Easy. And next. Okay, for this one, CRBFR, okay. The systematic name. Okay, what I would do is I would draw it first. So we have fluorine. So of methane, there's only one carbon. Then we have trifluorobromine. But due to the general naming convention of IUPAC, you have to order it from alphabetical first. So bromo is first, then it's just trifluoro. Bromo trifluoromethane. There you go. Okay, for this one, you have to look. See, look, if there is a free radical on both sides, that means it is still in the propagation phase. If there's a free radical in the reactants, that means it's in the termination stage. If there's a free radical on the products, then it's initiation. So first, anyways, at first it goes initiation, then it propagates, and then it terminates. You gotta memorize. So initially, free radicals are produced in the proper um, in the propagation stage. Uh, the free radicals substitute uh, with other compounds to produce more free radicals. So there'll be free radicals on both sides. In a termination stage, it will the free radicals will combine and become Cl2. An example of this will be the positive carbocation we did before. I mean, this carbo, the one we did. Basically, this is when it combines, it will produce C. What's it called? CCHHH. It'll produce basically it'll be a bunch of hydrogens, and this from here to here is termination. It combines to produce no more free radicals. Okay. Step 1, this is free radical substitution, and like we said, it needs UV light to react. Okay, so we have CLBR, and ozone depletion is from O3 to O2. So yeah, just write it out. You just write it out, then you just balance it. Make sure you put it to gas, very important. The one that acts as a better catalyst is the one that has the lowest bond energy. So the one with the lowest bond energy is 285, which is CBr, and the only, and I'll show you CBrF3 or CClF3. You will choose CBrF3 because it has the lowest bond energy. Okay, that's it. Next question. Okay, the systematic name of the above isomer. Okay, easy. First, you count the longest chain, so it's gonna be, whoops, it's gonna be one. That's 1, 2, 3, 4, 5, 6, 7, 8. What is 8? And it has no double bonds, so it's octane. And then you count, now you look for the branch chain. What is the branch chain? It's at this position. At what position? 1, 2, 3, 4. So it's 4 ethyl, since methane ethane, it's 4 ethyl octane. The reason we don't count from this side is because it might get confusing. I don't know, that's just the name, that's just the standard naming of it. You always take the lowest amount of carbons for the branch chain. Okay, next. The use of large alkanes are limited. This is why decane. Decane is decane. That's like C10H22, I think. It undergoes cracking to produce propane. Yeah. So the name of the process is cracking. So it's from an a huge alkane to a smaller alkane. That's cracking. And the catalyst for this process will be. It is the most common is aluminum trioxide at 650 degrees Celsius. Yeah. Okay, next. Okay, this is a lot. Okay, propane undergoes free radical reaction with bromine to produce one bromopropane. So what is this? Free radical. This is UV light. Easy. So this is free radical substitution. Okay, the first step in the reaction. Okay, so I think I drew this before, but propane with bromine. The first step that happens is that each electron goes to each of the bromine. And what is this process called? This is called homolytic fission. Yes, homolytic bond fission. And it is very important that you draw the arrow with only one side of the arrow there. Draw this. This one, that is not, this is heterolytic fission. This is wrong. This is wrong. That's for heterolytic. So for homolytic fission, it's only this. And in free radical substitution, there's only really one arrow, which is this. And yeah. So yeah, that's homolytic fission. Yeah, produces a radical. Next, the yield of the reaction is 30%. Which of the following best explain the yield of it? Okay, yes, the yield is only 30% because the product contains a mixture of hydrocarbons. I mean, there's nothing really much of it. One bromopropane is actually pretty stable. It's not that hard to form. The reaction is not slow, but it's regular. It's a regular reaction. It reacts readily with UV light. CBr bond is hard to break. The thing is, I guess, but CBr, we're not breaking the CBr bond. We are only breaking the CH group in the propane. So look, in propane, same thing happens. Homolytic fission occurs between the two things. So this will become, the carbon will get a positive electron, the hydrogen will become an electron. And we're not breaking a CBr, we're only breaking a CH bond. So CBr's bond is wrong. Okay. Calculate the volume of one propane gas produced at room condition, 5 grams of propane using the percentage yield above. So only 30%, see look, this is 30. So only 30% is produced from the reaction. So what I would do first is I would write the reaction first. So so we have C3H8, an alkane reacting with bromine in the presence of UV, it will produce C3H7Br plus HBr. And the reaction is already balanced, you don't do anything. Okay, now we want to find the volume of C3H7Br that has been formed. How do we do this? Since, okay, so first you want to find the number of moles of this. If we find the number of moles of this, doesn't this mean we can find the moles of bromine, C3H7Br, and HBr? Yes. Okay, so let's find the number of moles of C3H8. So it'll be 5 grams divided by the molar mass of C3H8, which is 12 times 3 plus 8, will give you 44. And this will give you 0.1136 mole. So if this has 0.1136 mole, doesn't this will have 0.1136 mole? Yes. Now this is only in mole. We want to convert it to volume. How do we do that? Since it is in room RTP conditions, it will be 24 decimeter cube. So it will be 0.1136 times 24. And this will give you around, wait, give me a second. Oops. So it'll give you around 2.7264 decimeter cube. And but they're saying that only 30% of this is formed. How do you do that? You multiply by 30 over 100. And you will get 0.81792, and when you round it, you get 0.82. That's that. Nothing too hard, nothing too crazy. Question number 8. Question number 8, okay. Okay, and CnH2n. Okay. Given below are the structural formulas of R, T, and Z. Given the general formula, give the general formula of alkenes. What is alkenes? It's the same as cycloalkane, so it's just CnH2n. Easy. Okay. Um, choose a type of hydrocarbon an alkene belongs to. An alkene has a double bond, and a double bond result in an unsaturated hydrocarbon. Unsaturated means there's double bonds. Okay, this is one thing. If there for alkene R, if there's two groups on opposite sides but they're in like different levels, then you call that a trans butene. If it's on the same level, then you call that a cis butene. So this will be trans. But these two must be the same. That is the only exception. And then this must be the same as well. They'll give you a cis butene. And this one is simply just propene. Nothing too much. Okay. I find a type of compounds R&T isomerism. This is going to be geometric isomerism, I'm pretty sure. Yes. R&T is on different levels. It'll be geometric isomerism, stereo isomerism. When an alkene is bubbled into an orange solution of bromine water, the color disappears. Okay. What is this reaction? This reaction is an electrophilic addition reaction. So an alkene reacting with a halogen will give you a halogenoalkane. A halogenoalkane. Okay. Now, choose a type of reaction between alkene Z and bromine. This is an electrophilic addition. Name the product of the reaction described. Okay. See, we have, let's say we have an alkene. What is the alkene? What is alkene Z, first of all? Alkene Z is propene. Okay, let's draw propene. So you have CH3 here, H, plus Br. So what happens in this reaction? In this reaction, the double bond will attack the bromine atom here. And then the single bond here both electrons here will move to this bromine atom. As a result, this becomes positively charged, this becomes negatively charged. After that, this bromine will attach to this bromine atom will attach to the one that has the least. Remember this is I don't think Markovnikov's rule apply here, but it attaches to any of the carbon. So yes, after it does that, the double bond breaks and the bromine atom attaches here. What do we have left? We have a negatively charged bromine atom. So and this is a positive. Then the bromine will just simply go here and attach to this. to become Br. Then all I have to do is just name the reaction. So we have methane, ethane, propane, and then we want to take the branch with the yeah, so it'll be 1 2, not 2 3, 1 2 dibromo propane. So yeah, it'll be 1 2, and chain 1 and chain 2 there's 2 bromo in the propane thing. Yeah, that's how I name stuff. Yeah, that's pretty easy. It's nothing too complex yet. I can just erase the whole thing. Okay, question 9. So it's a pretty big question. So yeah. Okay. Let's do this. Okay. 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 So first for this question, we must give the systematic name of the compounds 1, 2, 4. So what compound do we have here? It looks to me we have a methane, ethane, propane with a propene molecule with branching at, so it's going to be 2 bromo, no, 2 methyl propane, because the methyl group is in the this group. Are they asking for that? No. Okay, well, okay, so 2 methyl propane. So yeah, 2 methyl propane. Now when an alkene reacts with hydrogen, that's hydrogenation, right? So let's draw it first. Whoops, let me just make it a bit more clear. CH3 and CH3 here, and we have 1 hydrogen and 1 hydrogen. In hydrogenation, the double bond breaks, and this is an addition reaction basically, and the end product you will get um, you'll get propane. You'll get the propane group. You get propane, 2 methylpropane. You'll get 2 methylpropane for the first. So double bond breaks, and the hydrogen attaches to any of the carbon that are free. So it's 2 methylpropane. Yes. Okay, for the next one, for reacting with bromine, this is the question we did before. The double bond attacks the bromine molecule, and each bromine attaches to each side. And as a result, you'll get what's it called? You get a propane molecule. Let's do with alphabetical order first. So 2, 1, and carbon atom. Ooh, and carbon atom 1 2. So it'll be 1 2 dibromo 2 methyl 1 2 dibromo 2 methyl propane. So you start with alphabetical order. So bromo, then methyl, then propane. So 2 bromo, 1 2 bromo dibromo 2 methyl propane. 1 2 dibromo 2 methyl propane. There you go. All right, next. So, for the next reaction with HBr. Okay, this is an interesting reaction. This is hydrohalogenation of alkenes. It's basically the same concept as this, but now Markovnikov's rule will apply here. What is Markovnikov's rule? So Markovnikov rule explicitly states that the halogen will always bind to the positive carbocation with the least amount of hydrogens. Okay, so same process. Let's say we have a HBr here. Double bond. Double bond will attack the hydrogen. Then both the bromine will go to both the 2 electrons will go on the bromine. This is electrolytic fission. As a result, the hydrogen will break the double bond, and it'll attach to the one with the most amount of hydrogen. And then what's left is bromine. And what does this react with? It reacts with this positive carbocation. And this will give you the major product according to Markovnikov's rule. So Markovnikov's rule just tells us what product will be the major product. Okay, so simple. Well, now you have to just name this compound. This is just gonna be propane. 2 bromo 2 methyl propane. There's in the second carbon there's a in the second chain second carbon there's a bromo and there's a methyl. So it's 2 bromo 2 methyl propane. Easy. And then for the minor product, you just switch them around. Minor product, you just switch them around. So bromine will attach. This will be anti. So that will be anti. It will be like opposite for the minor. And this will give you 2 bromo. No. How do you name this? It will give you 1 bromo 2 methyl propane. Yeah. Okay. See, simple enough. Nothing too hard. Okay. What type of species is produced in the mechanism to produce compound 3? Okay. In compound 3, what do they want? Species produce type of species. Oh, so they want the intermediate. So during the intermediate of this, and the hydrogen has already bonded with the one with the most hydrogen. Let's take the one of the most, what's it called? The one of the most. Let's take the major product for example. We have a positive. I guess they're talking about compound 3 to produce compound 3. In compound 3, there'll be a positive carbocation. They're asking what type. For type, you just look at the amount of R groups. So we have an R group here, another R group here, and another R group here. What does this give us? This gives us a tertiary carbocation, which is very stable. Give the complete name of the type. Okay. Apparently all of them are electrophilic addition, but I don't really agree with compound 1 since I feel like it's catalytic addition. It's not electrophilic. I mean, that's what Google said. But I mean, I guess I don't know if the question's wrong or not. But let's just say it's electrophilic addition. Okay, for next question. Question 4. 2-methyl propane. Let's draw it first. Let's see, we have the methane, ethane, propene. Propene is in the that one. 2-methyl propene group. Okay, let's draw propene first, and then 2-methyl. So on the second carbon there is a methyl group here. Hydrogen and hydrogen. Okay, it undergoes oxidation with KMnO4 to give different products on the concentration. Okay, if it is reacting with cold and dilute KMnO4. Here, let me just redraw that to make it easier. It will be CH3, CH3, H3, CHH. If it is reacting with cold and dilute, if halogen alkane is reacting with cold, dilute, the double bond will break and an alcohol is produced. So if the double bond breaks, two OH groups will bind, one OH group will bind to each carbocation, which will give you C4H10. So 1, 2, 3, 4, 3, 6, 7, 8, 9, 10. C4H10, O2 to oxygen. Okay. Next, give the organic compound if it is reacting with a hot oxidizing agent. Okay, so we have CH3, CH3. Two products are actually formed from this reaction. This is an R group and two R groups with hot KMnO4 will give you a ketone. A ketone with two R groups with R1 and R2 respectively. So it'll be R1, R2. Let's say this is R1, this is R2 as well. And then this group will produce CO2 plus H2O. But is carbon dioxide or water organic compound? No, it's only the ketone group. Okay, and what is R1? We said R1 is going to be this, the top one, which is CH3. And the bottom one will be CH3 as well. And then you just count the number. So it'll be 1, 2, 3, 3, 3, 6 hydrogen, and 1 oxygen. Pretty easy. Okay, so question 10 now. So this is a pretty hard question. It's not really that hard. So limonene is a natural oil found in the rind, which just the formula is given below. So for the molecular formula of limonene, you just have to count the number of carbons and see the amount of hydrogens. I have There's maybe no other way to do it other than that. So this would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there will be 10 carbons, and then 3 hydrogen will be in the top here. There'll be 3 here. This is all bonded. There's 2. There's 2. Another one. This is 1, 2, 3. There's 1 right here, and there's 2 right there. 1, 2, 3. There's a hydrogen. There's a hidden hydrogen there. This is 3 right here, and this is 2. So how much is there? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. C10H16. Okay, nice. Next one. Limonene reacts with excess HBr. Okay, this is what I explained before. The bromine will attach to the one with the least amount of hydrogen. So, so you want to focus on the ones that has a double bond group. So let's focus on the top one first. Let me just draw it out so we don't get confused. So when the double bond breaks, when it attacks hydrogen, the bromine will attach to this one, the one with the least amount of hydrogen, which is Markovnich's rule. And where's this? It's right there. So this is bromine. For the bond group, same concept. It's almost similar, but this is just hydrogen. So yeah, the bromine will attach to the one with the least amount of hydrogen, which is gonna be this one. And then you'll get that as that. See, similar. Okay. Next one. The complete name of this type of reaction when a limonene reacts with HBr is an electrophilic addition. Okay. Okay. Limonene reacts with hydrogen gas in the presence of a catalyst. The catalyst can either be nickel or platinum. Doesn't matter. Okay, so for the next one, get the number of moles of hydrogen that will react completely with 1.36 gram of. So they don't give you the reaction, but you must know that when any double bond breaks, there can't be a there can be there can't be technically there can't be two positive carbocations. A hydrogen will always bond to them to make them not positive. So there's going to be a hydrogen here when the double breaks, another hydrogen there, and a hydrogen here, and a hydrogen here. So that'll give us C10H20 after the double bond breaks. Okay, so C10H20. Simple now. Give the number of moles of H2 that will react completely 1.36 grams of limonene. Okay, so for limonene it's C10H16 plus 2 hydrogen will give us C10H20. It's 2 because you have to balance it out. Okay, so simply they only find number of moles. How do you find number of moles? 1.36 grams reacting with say 12 times 10 plus 16 is 136. It'll give you 0.01, and then the number of moles is 0.01 times the amount of moles, 2, so it'll be 0.02 moles right here. Easy. Limonene reacts with acidified hot concentrated oxidizing agent. Okay, so limonene, let's focus on the top group first. So we have an R group here, did they say hot acidified KMnO4? Oxidizing, yeah, same thing. Yeah, an oxidizing agent, it's the same. So we have CRR, double bond to CHR. You know that this will produce a ketone, C double bond O. And what is a ketone? A ketone is a carbonyl group. So one carbonyl group is produced from the top. And what about this one? This turns into an aldehyde. Yes, this will turn to an aldehyde, which then further oxidizes into a carboxylic acid. So from the top, one carbonyl group is formed, and one carboxylic group is formed, or carboxyl group. This is a carboxyl group. What about the bottom one now? Bottom one this produces a carbonyl group as well, a ketone group, and this will produce CO2 plus H2O. You must be careful if it's hot or cold. If it's cold, if it's a cold oxidizing agent, then it'll just produce an alcohol. But if it's a hot oxidizing agent, then it'll produce uh, three types of products depending on the groups. Okay, so yeah, so two carbonyl groups are formed, one carboxylic group is formed, and carbon dioxide water is formed. So yeah, CO2 gas is produced. That's right there. Two carbonyl groups, yes, and one carboxyl group, yes. Okay. Question 11 now. Okay, so another type of these questions, lavandulol, fragrance found in lavender. Okay, molecular formula, like I said, there's no general formula, so you just have to count. So there's gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there's 10 carbons. So BC10, and count the amount of hydrogens. 3, 6. So there's 6 up there. 1, 2, 3. There's a hidden hydrogen here. That'll be 7. There's 2 hydrogens there. 1, 2, 3. Another hidden hydrogen. Oops. Another hydrogen. Hydrogen here. There's 2 hydrogen here. 1, 2, 3, 4. C. There's 2 here. And there's 3. So there's 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. There's one more. So there's 3, 6, 2, 3, 4, 7. So that's okay. Up there is 7 plus 2. 7 plus 2 is 9. And then 1, 2, 3. That's 10. So this one is 10. 10, 11, 12. Plus 2 is 12. 15. Wait, that's 12. And then this one is 13. Oh yeah, okay, 13 plus 16 plus 2 will give you 18. Okay, there we go. I forgot to count the hydrogen here, OH group. Okay, nice. Choose, and then there's one oxygen as well. Yeah, okay. Choose the best answer for the comparison of the angles A and B. So, I think we learned in AP, but a double bond will repel more than a single bond. So that's why angle A is less than angle B. So yeah, because angle B repels more, so it's a larger angle than and angle A is shorter. So yeah. Okay, next, which of the following is true about lavandulol? Lavandulol has only optical isomers. Yes, because for it to have optical isomers, there must be a chiral carbon. And yes, there's a chiral carbon. Basically, all 4 groups are different. This group is different, this group is different, this group is different. There's a hydrogen, which is different. And so there's only one chiral center for this lavandulol, which is here. And this will give optical isomers. The reason it doesn't have geometric isomers because it has double bonds. I mean, it doesn't have geometric isomers because the groups are not the same. The groups are not the same. You can't have, like, from the you can't have a cis and trans of CH3 here because CH3 doesn't exist here, either here as well. It's only hydrogen hydrogen. So yeah, you can't form cis or trans there. It only has optical isomers. Okay. Lavandulol reacts with HBr and bromine to give a saturated compound. Okay, with bromine, there's 3. So yeah, you just have to replace, just break the double bond. So let's say just X that, and then just produce more. Destroy the double bond, and then you're gonna give Br, H, H, another Br. Okay, so just count. So we know there's a chiral center here. This is not a chiral since these 2 are grouped. That's CH3. For this one, 1, 2, 3. This is a chiral center. So yes, that is a chiral center. So that's a chiral center. This is a chiral center from before, and this one, this is a chiral center since there's CH3, CHBr, and this group here. So three different R groups. So there's three. Now for this one, the question is wrong. There should be only one. Only one. I'm not gonna waste my time doing it, but you can do it yourself. You can attach the bromine to the carbon cation by breaking the double bond and attaching it to the least amount of hydrogen. But I've tried a lot of times, and in my experience, I've only gotten it. There's only one uh, chiral carbon. Even Gemini and ChatGPT said so. I don't know. The question's wrong probably. Now, oh, this is a good one right here. Lavandula undergoes oxidation with a hot concentrated acidified oxidizing agent. Which of the following products are not possible products of reaction? To find the products that are not possible, we must find what formed. Okay, simple. It's not really that simple. Okay, let's take this group. We have a C double bond, and we have two R groups. Let's say this goes to an R group. This is R1, R2, this is R3, and this goes to a hydrogen. In hot acidified KMnO4, doesn't this separate and turn into a ketone? Yes. So this a ketone will be formed here. What about this group? R3 and H. This will produce an aldehyde, which then further oxidizes into a carboxylic acid. So D double bond O, C double bond O into OH with the R group. So you can draw it on the diagram that it's gonna be uh how would I draw this? Um I guess you could say the bond broke here, and okay, so basically what I'm trying to, so this part goes out. It's somewhere here now. It turned into a ketone. So this is out of the reaction. That group is out of the reaction, and the double bond is gone. Um, so it'll be R1 and R2. So this is out of the reaction. Next, it turns into aldehyde, which is should I do it there? Okay, so this breaks, and this becomes C double bond O and H, right? Remember the hydrogen here? So yes. So become a C double bond O and H. And then it further oxidizes into C double bond O OH to produce a carboxylic acid. Okay, that's group 1. That's the first double bond done. Now we can look at the bottom one. Um, got C double bond C, H and H. Where does this go to? This separates and becomes what? CO2 plus H2O. That's easy. And the other one, this side, is attached to two R groups. So what does it become? It becomes a ketone. So, ketone, what is a ketone? It attaches to here. Oh, did I say aldehyde in the first one? Oh no, my bad. Forget it. Okay, let's focus on this one. This becomes a ketone group. Wait a minute. Okay, that reacts. Okay, well, I think it's more better. Okay, see, C double bond C. This is gone. Okay, this whole thing is gone. It turned into carbon dioxide and water. And then this it becomes a ketone by adding a double bond here. Wait a minute. Yeah, it becomes a ketone, and then the R group attaches here. Okay, look, C double bond C. It's two hydrogens. This is here. This separates and becomes CO2 plus H2O. while this side it has two R groups. And what does this become? It becomes a ketone, C double bond O. Given the first R group is going to be CH3. What's the second R group? It can be the whole entire molecule. So what will this become? This will become double bond, double bond O. So yeah, this is the C we're talking about here, right there. So it'll be a C double bond O, and then it's gonna be CH3 here, and the whole R group right there. Okay, yeah, that's it. Now you don't forget about this one as well. Uh, this one, how do I say it? It's for this one, it's the basically alcohol gets oxidation of alcohol. Yeah, it's in chapter 4, I think, of alkynes and ketones. So basically we have an alcohol here. I'll say this is an R group, and the OH group is right here. Okay, well, actually let's put it on top. It feels better on top. Okay, let's say we have a, okay, so when you oxidize alcohol groups, what happened? Two hydrogen get eliminated. The first hydrogen will be from here, and then the hydrogen will be from here or down. It doesn't really matter. And what will be produced? A C double bond O. C double bond O H. And what does this look like to you? Oh, maybe I don't think you can see it, but wait, let me just start it. The whoops, no, it's not a C double bond O. The hydrogen gets removed and becomes a C double bond O, and the one hydrogen gets removed from the left side, and this becomes H. Isn't this an aldehyde group? Didn't we say that aldehyde groups can further oxidize into carboxylic groups, right? So this will further oxidize into a carboxylic group. So easy. So yeah, so you take the hydrogen out, and you remove one hydrogen there, and you produce a double bond here, and this will produce an OH. There you go. You have the structure. Okay, in the end, you're gonna get something like that, and I'll draw it to simplify it. Okay, let me just simplify it now. This will be, I've written it down, it will be C double bond O, carboxylic group, which then moves into uh, that carbon, it moves into the chiral carbon in the center with double bond O into CH3. This is a hydrogen to it, and this will be another carboxylic group. Okay, this is what you should get as your end product. Okay, now which of one are not possible? So which ones do not look like this? Okay, so let's, okay, yeah. Remember when CH produces carbon dioxide? Yeah, that's the possible, that's what it produced. Okay. Now this formula is this actually. So CH2COOH is gonna be this one right here. And then this is the chiral carbon is right here, I think. CH3CO. This is CH3CO. Chiral carbon attached to a hydrogen, and then a carboxylic group right here. CO, oh yeah, my bad, OH. And these, you won't get them. Even during the reaction, like when it's separated, you'll get none of these. Okay, and that's it. Okay, now it's gonna be question 12. Oh, how long is this recording? 5 minutes. Okay. Question 12. Given terms of N as number current, the general formula of alkanes. Easy. General formula of alkanes is going to be CN, H2N plus 2. Nothing too crazy. Reaction 1, reaction 2, reaction 3. In reaction 1, there's UV light. What has UV light? UV light, I mean, free radical substitution. So it'll be free radical substitution. In reaction 2, if we have ethanoic NOH, this is a very important. If it's ethanoic NOH, it will be elimination. Else, if it's aqueous, then it will be substitution, nucleophilic substitution. Else, it's going to be elimination. So yeah, ethanoic NMH will give you elimination. Reaction 3. What is this reaction? Oh yeah, this is what's it called? The hydration, the catalytic hydration of alkenes. It uses phosphoric acid at 300 degrees Celsius at 60 atmospheres, and what you get you'll get an alcohol. So from an alkene to an alcohol, it's going to be hydration, catalytic hydration, catalytic hydration. Yes, I think. Yeah, okay. So it'll be electrophilic addition. Reaction 3 produces two isomers. Give the systematic name of the isomer of C. Of the isomer of C. Reaction 3. This is I think they just want to name propane 101. Wait, what? Uh, Reaction 3 produces two isomers. Propan 2-ol and propan 1-ol. Give the name of this one. I guess they want the name of the other isomer. Oh yeah, they want other isomer of C, which is propan 1-ol. So the OH group will just be right here, not there. Okay, yeah, that's a bit weird. Why is compound C the major product? The reason compound C is the major product because in propan 2-ol, you'll have two R groups in the intermediate, and you know the higher the level, the higher number of alkyl groups or R groups, the more stable it becomes. And things in life, we always like stable things, so that's why it prefers this reaction more than propan 1-ol, because in propan 1-ol it's only a primary, right? So a primary will be this R group and HH. This is a primary. In propan 1-ol, this is unstable. It's the least stable basically. It's not really unstable, but it's just the least stable out of all. So yeah, the secondary carbocation. And a tertiary, you'll never get a tertiary from this isomer, I'm pretty sure. So yeah, you'll never get a tertiary. Select the repeating unit of polymer D produced. Okay, so for polymer D, so yeah, you just break the double bond and it's nothing too crazy. CH3 is here, hydrogen, CH, yeah, just break double bond and you attach single bonds. Yeah, it can be other way around, doesn't really matter. Next, compound C can be produced from compound A. Okay, yeah, this one, aqueous NaOH. What is that? That is nucleophilic substitution. Why is it called nucleophilic substitution? Because the nucleophile replaces chlorine, and this will become OH. Yeah, nucleophilic substitution. There you go. Yeah, okay, nothing else. Question 13. Okay. Give the name of polymerization produced. Okay, so there's new products formed. Like if more stuff are being added, that's gonna be addition, polymerization. Bonds broken between the above. Okay, the original, it had C double bond C, right? One pi bond is broken from here, and two sigma bonds. And two sigma bonds are attached on each side, are formed from each side. So C is C. So yeah. What is that? Pi bonds and sigma bonds are formed. Give the systematic alkene A as butene. If you want to know why it's not butene, butene depends on which carbon atom the double bond is formed. So in butene, the bond is formed on the first carbon, but in butene, the double bond is formed in the second carbon, right here. See, 1, 2. That's why it's called butene. But here, it's just butene, nothing too crazy. Including A, okay. How many isomers does monomer A have? What is monomer A? Okay, we can write monomer A. Monomer A will be Cl bond C with C2H5, hydrogen and hydrogen and hydrogen. Okay. So first of all, you have the geometric isomers, which is cis and trans, right? So you have CH3 here, CH3 here. This is trans, or you could have a cis, which is up top. So that's two already. For structural, oh, oops, how do I, whoops, okay, let me just redraw it again. C2H5, H, H, H. As I was saying, it has two, since it can do cis and trans. And then it has a structural isomer uh, of like, what's it called? 2-methylpropene. This is the next isomer. So it's going to be 1 plus, what else is there? You can also turn it into a cycloalkane, since they have the same general formula. You can see that C C C C. That's another one, and then one more, the isomer of this cyclo, which is C C C, and then bonds to anything CH3. So it's 1-methyl cyclohexane, and that's another isomer, so it's plus 1. 3, 4, 5. There's supposed to be one more. What is the last one? Uh, that's 3. That's 5. The last one will be butene, butene. Oh yeah, butene. No, butene. That's another structural isomer. So it'll be 6 in total. 1, 2, 3, 4, 5. Yeah, that'll be that. All right, next. What did it say? Okay, I think it's that. Yeah. Okay. Next, alkenase. Alkene, if added to HBr, produces two isomeric products. Oh yeah. Okay. So it'll be C2H5, H, H, and H. So what happens is, as before, the double bond breaks, and the bromine will go to the one with the least amount of hydrogen, and this will go. This is for the major product. So it's gonna be 1, 2. So it's 2 bromobutane, or when this goes here, it's gonna be 1 bromobutane for the minor. Markovnikov's rule. Okay, next one. Reaction was uses hot concentrated oxidizing agent to give one product only, ethanoic acid. Okay, let's backtrack. Ethanoic acid. Isn't this a carboxylic group? Right. But doesn't this come from aldehydes? Yes, it does actually come from aldehydes. And from which group does this come from? This will come from a CH group, CH3 group up here, and a H group that will bond into some carbon. So what is the only geometric isomer? I mean, what is the only isomer that has a CH3 here and is the formula is C4H8? It's gonna be butene. I'm pretty sure they meant cis-butene or trans-butene here, but I don't know. Yeah, since cis and trans can form the same thing. And okay, and if you're asking that, yeah, this isn't C2H5 also, oh my bad, oh, that's, isn't C2H5 produce an aldehyde as well? Yes, it does, and it does turn to carboxylic. But remember, they said only one product only. See, in here, this will produce CO2 and hydrogen and H2 water, and which is not one product only. If you do that, that will be only one product. Okay, that's why it's only cis or trans butene. For the next one, select the correct polymer produced in a reaction 2. Okay, you just since we know that's butene, you can just simply break the double bond. Oh yeah, let's just break the double bond, and it can be here, it can be there, it doesn't matter. And then two single bonds are formed. So pi bonds broken, and two single bonds are formed. Okay, easy. For question 3, C double bond C, CH3, CH3. Give the systematic name of product R. So this is a hydration of alkenes. It'll be with phosphoric. The catalyst will be phosphoric acid at 300 degrees Celsius and 60 atmospheres. What happens is the double bond will break, and the OH group will either go here, or here, or here. It doesn't really matter. I'll give you the same product anyways. So yeah, if it goes there, it'll be butane to all. If it's there as well, it'll be butane to all. It doesn't really matter. This will be electrophilic addition. Yes. What is the type of intermediate produced in the type of intermediate produced in this reaction will be a secondary, because on both atoms, both carbocations, there is one R group here and a second R group. Same goes here. There will be an R group here and another R group. So it's two R groups, which is secondary. Yeah. Okay, that's not that bad. 15 now. Okay, choose a type of species in the second step. So they're talking about this second step. You know that uh, NaOH, OH is the nucleophile, and that is a type of species we want. Not this, but it's usually the one that is reacting with it. That's what we name it. That's what the species is. So it'll be a nucleophile, which is OH. Next, whoops. Select the carbocation that is not possible. Okay, so for this question, oh, my computer is lagging. Okay, for this question, all they did was just, they just moved it this way, like one rotation. I don't know how to say it. One something. Okay, I'll just draw it so you guys can understand. So all they did was just flip it. So it was the double bond will go there, and another double bond will go there. They said take the carbocation that is not possible in reaction 1, HBr. So it doesn't really matter where Br goes because they have the same amount of hydrogens. So let's say we remove the double bond right there and a double bond here. It's a very sophisticated thing. Okay, let's just say it's okay. So the question looks like they attached the bromine to the top. If you attach the bromine to the top, there cannot, and there can absolutely cannot be another positive carbocation here because it has already been bonded by the hydrogen. It can only happen on the other side. So it can happen here, bromine plus, or maybe plus here. Doesn't really matter. Yeah, see, look, see, yeah. can be on the same side, on the same double bond, but it can, but on the other side it's completely fine. Plus here or plus there. Let me just erase it. Plus here, so there's to be a double bond here, double bond here, double bond here, double bond here, but they destroyed it, and yeah. Okay, IUPAC name for isomers A and B, where A has a functional group closer to each other. What are we? Oh, okay. So after that, after that reacts, see this in there. It reacts with OH and excess NaOH. I'm pretty sure this is probably most likely electrophilic addition. Is it? Yeah, this is electrophilic. This is aqueous NaOH. I'm pretty sure. I don't know why I didn't specify, but it's electrophilic addition of NaOH. But it's two. This will turn into an OH group, and this will turn into an H group, and I just name it. So it will be cyclohexane 1. The first bromo is in the first. Oh, my bad. Yeah, I forgot. This also gets replaced with a hydroxyl group. Yeah. So, and this will be replaced with the hydroxyl. This will be replaced with a hydroxyl group. Alcohol group. Yeah. Okay. Whatever. So it'll be on the first. There's gonna be a H 1, 2, 3. There's in one position 1, 2, 3. There's diol. On the other one, it's 1, 2, 3, 4. So this is 1, 4 diol. And I just named the compound cyclohexane. Question 4. What kind of oh yeah, if it's ethanoic NaOH, then it'll be elimination. This was aqueous NaOH. They should have specified it, but it's fine. Aqueous NaOH will give you nucleophilic substitution, while ethanoic NaOH will give you elimination. Just remember that. And elimination will produce something else, like NaX plus H2O as well. Question 16. Okay, this one you just have to know, I guess, like, just name the compound. So it's methane, ethane, propane, butane. Chloro is on the first branch. 2-chlorobutane. Take the longest chain, methane, ethane, propane. And there's a 2-chloro, 2-methyl. And you take the longest chain here as well. Methane, ethane, propane. Propane. Oh, my bad. You take methane, ethane, propane. 1-chloro, 2-methyl. Yeah. Because if you count from down to bottom, it don't really makes sense. I don't know how you would call this group. So you just count it from here. So methane, ethane, propane, and this is CH3. So it's propane group, 1-chloro, 2-methyl propane. Okay. Under certain conditions, 2-chlorobutane gas undergoes elimination reaction. Elimination reaction, what is that? Ethanoic NaOH. When the elimination reaction occurs, two structurally isomeric products are formed. Okay. 2-chlorobutane. Let's see. Methane, ethane, propane, butane, and there's a chlorine atom here. Okay. Yeah, so elimination reaction. Okay, an elimination reaction is from an alkane to produce an alkene, I think. Let me just confirm real quick. Oh, whoops, no, a halogenoalkane to be specific. It'll turn from a halogenoalkane into an alkene. And how does it do that? Well, it does. So, when it reacts, the double bond can either form here or it can form here. And they only ask for any. So let's just do but1. This is but2ene. And another form is here. So let's just say but1ene. Whoops. Right here. This is but2ene. Okay, yeah, that's nothing too crazy, nothing too hard. 2-chloro 2-methylpropane on nickel substitution with Cn. Okay. Um, let's draw the compound first. Propane, yes, propane. So it's Cl 2-chloro. Oh, yeah, there we go. So yeah, so 2-chloro 2-methyl propane. And goes ethanoic KCN. What happens? We did this reaction before. Cn substitutes with Cl to give what? To give by increasing the carbon chain, producing there. But they said, what is the type of mechanism? Okay, so during the intermediate, don't we have a tertiary carbocation? Yes, we do. So 1, 2, 3. And what does tertiary go to? Tertiary goes to an SN1 reaction. So this will produce CN. And for nitrile groups, you always count from the nitrile group first. So it'll be methane, ethane, propane. So it'll be propane, what do you call it? 2,2 dimethyl propane. Nitrile, don't forget the nitrile group at the end. Okay, nothing too hard. Question 17, the last one of the day. Um, 1-chlorobutane is hydrolyzed in the hot alkaline. What is the type of mechanism? Okay, so an alkyl alkane to turn into an alcohol. Um, what is the reaction called? Uh, something oh yeah, nucleophilic substitution reaction. This is a nucleophilic substitution reaction. So butane, methane, ethane, propane, butane with chloro here. One chloro is on the first carbon, first chain, first carbon. Okay, so what is the correct type of the reaction? So when it does nucleophilic substitution in the intermediate, this will produce a positive carbocation. And it looks to me there's only one R group here, so this will be primary. And what does primary always go into? It will always go into SN2 reaction. Which of the following is true about the reaction? The concentration of both, okay, for an SN2 reaction, the concentration of both reactants affect the rate of reaction. But for SN1, only one of the reactants will affect it. But for SN2, it's both. I guess you could see, look, SN2 relies on two products. SN1 relies on one product. And this is the intermediate step. Yeah, so the OH will just bind to that, and this is gonna turn out, get out. So this is coming in, this is getting out. This is for SN2 only. Okay. Next. C4H9Cl has 4 isomers. One of them is 1-chlorobutane. Give the IUPAC name of the isomer that will undergo a substitution reaction and produce the most stable. What is the most stable? The isomer that has a tertiary carbocation. So we're looking for a isomer that has a tertiary carbon. Which one is that? That will be this isomer. See, when it undergoes substitution during the intermediate, it is a plus, no? And it has 3 R groups. 1 R group, 2 R group, 3 R groups. I'm not writing the hydrogens because it'll take a long time, so just pretend there's hydrogen there. But it will produce a tertiary carbon, which is the most stable. Give the IUPAC name of the isomer that has a chiral carbon. So this is just trial and error. But afterwards, after a long time, you will eventually find that this what is it? Oh, my bad. It's 2-chlorobutane. What is that? That is gonna be. You just have to keep trying and see when it has a carbon. What is a chiral carbon? A chiral carbon is when it has four alkyl groups. I mean no, four different R groups. So in 2-chlorobutane, you have an R group here, which is different from this, and this is different from this, and that is different from this. So this is the chiral carbon. Of a branched primary isomer. So they're asking for a carbocation that is primary. And after a bunch of tinkering, you will get this. Say this is hydrogen, this is hydrogen. There's only one R group here, which is gonna be this. It's positive. So that's a primary. So this is the reaction. Okay, next. Chloralkane has a following mass, percentage by mass. So yes, chlorine 7.02. Okay. For this, we have done this many times. I'll just start down. So we have Cl, H, and carbon. And Cl is 71.72. And hydrogen, you have 4.04. And that you have to do 100 minus that. 100 minus these two. So you'll get 24.24. So yeah, you put the percentages first. So you do this, then you put the percentages there. Afterwards, you divide it by the molar, not the molar, yes, the mass of the atom. So chlorine has a mass of 35.5. So we're gonna put 35.5. Hydrogen has only 1. Carbon has 12. Divide it and you'll get 4.04. This is gonna be 2.02, and that's 2.02 as well, I'm pretty sure. 71.72 over 35.5. 2.02, 3 significant figures. And then you divide, with the lowest amount. You'll get 1, 2, and 1. So yeah, you'll get C, H2, Cl. But it's not done yet. Didn't they say that the molar mass of the compound is 99 grams? That's very important. Okay, so first get the molar mass of this. And see if it is 99 molar. No, that's considered. Just see if it's 99. It's not right. You'll get 49.5. Okay, so what do we do? Simple. We do 99 divided by 49.5, and this will give us 2. And then you multiply this here. As a result, you'll get C2H4Cl2. And that is what you need. Next, we'll get the IUPAC name of the isomer that's produced from the reaction with chlorine. With ethene, okay, ethene and chlorine, easy. With ethene, when it reacts with chlorine, the double bond breaks. And the chlorine just goes wherever it broke. So this will be 1,2-dichloroethane. And that will be it. That is nothing much in this quiz. Just have to memorize a lot. And I don't think this will come. No, this will probably come in MCQ for final. But yeah, that's the entire quiz. Thanks for watching.